Hello. We're going to do quantum today, coming to you from smoke-filled Berkeley. I don't know why we're going to have you shh, but there it is. Maybe I should do a woohoo, woohoo, woohoo. And here's the shh. And, oh, look. Yeah, it's quantum. So I guess the idea is those are electrons going around the letters, and there's two possible states they could be in the upper state or the lower state. Yeah, okay, well, that's quantum. There you go. There's the doodle for the day. So to start off, quantum sort of has this genesis in this notion of an electron being in possibly two states. For example, it could be in a ground state, or it could be in an excited state. So that was the picture we saw before, and we denote the ground state, say, by 0, and the excited state by 1, with this bracket notation. We'll talk a little bit more about that, but it's fairly clear. And really, electrons, sort of the quantum theory says that it's a superposition of being in the ground state and the quantum state. And in each one of those, you have these little numbers here, which are amplitudes. And amplitudes are actually complex numbers, right? They're complex numbers. And so they sort of are like probabilities, but they're not quite. But they do have this property that the sum of their squares is equal to 1, which is exactly like probability. So you can view, in some sense, their squares, the magnitudes of the squares as probabilities. So A0, A1 are amplitudes, and so when you measure a state in these funny superpositions here, what you can get is you'll get state 0 with probability 0 squared, alpha 0 squared, and state 1 with probability alpha 1 squared. Okay, so this all makes sense because alpha 0 squared plus alpha 1 squared is equal to 1. So amplitudes can be, when you measure them, they stop being these complex numbers, and you just get a result. You either get state 0 or state 1 as your measurement, and now you get a probability distribution on that measurement, on that set of measurements. You get state 0 with alpha 0 squared and state 1 with alpha 1 squared. Okay, so now that's one bit. Okay, so the classically, you could have a state which is 0 or 1. A quantum state, our internal view of a quantum state is it's this alpha, which is some amplitude on 0 and some amplitude on 1. Okay, so it's maybe it feels a little bit like probability, but it's a bit different because alpha 0 and alpha 1 are not probabilities. They are complex numbers whose square magnitudes add up to 1. So when you measure, you either get 0 or 1, just as you did in the classical state. So that's all fine. So it's two numbers internally, and the measurement yields 1 bit in some sense. Okay, so now if you have 2 bits, something more interesting happens. So in classical states, you have one of these 4 possibilities, just one of these 4 possibilities. And you know, this could be 0, 0 or 0, 1, 1, 0 or 1, 1. And the view of a quantum state is internally you have 4 internal numbers. And those internal numbers represent, you know, in some sense, a distribution over 0, 0, 0, 1, 1, 0, 1, 1. But also more. I mean, they're complex numbers, so they actually have, there's a bit more going on here than just probabilities over those 4 states. But essentially, the internal state, in our view, for 2 bits corresponds to 2 quantum bits, corresponds to 4 different numbers. So even if those numbers only had precision of 1, the 2 bits becomes 4 numbers, or 4 bits at least. So in some sense, these are this representation, these alphas give you more power in some sense, or more issues. In fact, originally they gave you issues, and now you have the property of them is that the sum of the squares of all these amplitudes equals 1. It's 1 squared magnitudes. So you only ever measure 1, 0, 0, 0, 1, 1, 0, 1, 1. In that sense, it's the same as classical, in that each measurement only produces 2 bits, but our internal view of it is there's a lot more going on. In fact, there's 4 numbers that are evolving in some way in the system internally. Okay, so the measurement only uses till bits as it does for classical, but there are 4 internal numbers that are running around in secret in some sense. We can't, when we measure it, we only see these 2 bits. But in secret, these things are sort of running around in the system. Something new. Okay, this is something new in some sense with 2, right? You see something very interesting. Here you only had 2 numbers, and maybe as you get larger and larger, it's, more complicated things happen, and you get more and more of these numbers running around. But let's talk about one more thing. Let's talk about, you could look at 1 bit. So if you look at the first bit, you may get the result 0. You don't have to measure. When you measure, you don't necessarily have to measure the whole state. You could just measure this bit, this first bit here. And what you get is you get 0 with this probability, this 0, alpha 0, 0 squared, and alpha 0, 1 squared. Okay. Now, what is the state of the system if the result is 0? Well, it's either 0, 0 or 0, 1, right? And now, that means that these guys are no longer possible. So you still have an internal system with 2 internal numbers still running around here. But those numbers have now scaled. Okay, so now the state of the system is you have 0 for these amplitudes, and you have this is the state, right? You have alpha 0, 0 times 0 times bracket 0, 0, and alpha 0, 1 is the amplitude on the state 0, 1. And you scale the denominator, make sure that the sum of the squares is equal to 1. Okay, so this is what happens when you measure. Okay, so you can do 2 kinds of measurements. You can measure the whole system, you can get these things back, and you get this probability distribution over them, or you can measure one of the bits, and then what you do is you get sort of a collapsing onto all the states that are consistent with that measurement. Okay, pretty wild. It's a pretty wild sort of thing. Okay, so qubit 1 internal state. Okay, qubit is, 2 also has an internal state, alpha 0, alpha 1, and beta 0 and beta 1. Now the joint state, if you think of those 2 bits together, what does an internal system state look like? Well, it's just a joint distribution as you multiply the amplitudes, okay? You think of them as independent. This is sort of an independent joint state. Now the question is, let's think about this joint state. This particular joint state can be decomposed into 2 of these. But is that true for every possible combination of these 4 numbers? For every alpha 0, 0 and alpha 0, 1 and alpha 1, 0 and so on? Can they all be decomposed into the simple version where they're some function of alpha 0, beta 0? What do you think? And I guess the answer is you're not going to tell me because you're on the other side of a screen. But the answer is no. Okay, so let's look at this joint state. Okay, this 1 root 2, 0, 0, plus 1 over root 2, 1, 1. The root 2's make the sum of the squares add up to 1. So this is the exercise in the book, and so there's no solution to the system of 4 polynomial equations. In particular, what this says is that we have the condition that these alpha 0 times beta 1 is equal to 0. So once you do that, then you're already sunk, right? It means at least one of alpha 0 is 0 or beta 1 is 0, which means that at least this has to be 0 or this has to be 0. So that's really the proof. Okay, this is called a Bell state. Okay, it's one key to the power of quantum mechanics. it, again, this has this notion that here you know something. If you measure the first bit, zero here, the second bit you know what it is. You know that it's a 0. Okay, so this is a power and entanglement. This is one of the famous EPR, I guess EPR, Einstein, Podolsky, and Rosen. They sort of had this notion of two entangled electrons that are far apart. If Alice sees that the first one is in the ground state, Bob will also see, even though they're really far apart, that the electron is in the ground state, which caused enormous consternation. Okay, so it's more complicated a bit, but these are the famous Bell inequalities. This is a famous Bell state. You can look it up on Wikipedia. I spent the morning doing that. It's fascinating. Now, the internal state, again, is that you have one number. Let's review. If you have n qubits now, n is some arbitrary size. So this is an n-bit string. This is an n-bit string. There's the n-bit string. So there's 2 to the n different strings. Each one of these is an amplitude. And so they're complex numbers. Okay? The full measurement. Okay, so in the internal state, these 2 to the n amplitudes are running around doing what they will, right? Following their rules, the sum of their squares add up to 1. But when you actually measure, you can measure a partial part of it. You can measure the first bit and see that it's 0, and then it will collapse onto all the states where, if it happens to measure 0, it will collapse. You have no control where it collapses. It might collapse onto the part of the space where all the strings start with 0. It might collapse onto the part of the space where all of them start with 1, but that's the way it goes. So so this one yields, if you do a full measurement, you get a whole string back. You can just measure a substring up to k bits, and that will collapse the state so that the other bits behave as scaled appropriately. Okay. Now the reason this is interesting is this is how quantum works. When they have many particle quantum systems, to really understand how they work, you need to simulate them. And when you simulate them, you need to understand their internal state. And the internal state are these 2 to the n numbers, and we're going to watch them evolve in really fascinating ways. And when they evolve, you have to keep track of how they evolve. So you're keeping track of 2 to the n different numbers as they evolve. So this is problematic, right? So there's still no answer. He posed this question, and there was no answer. There continues to be no answer. It continues to be a challenge to simulate large systems of quantum particles. But what computer scientists did, in particular Professor Vazirani, was among them here at Berkeley. He's also the co-author of the book. Now, if you assume this action of a system of n particles, or a quantum system, what can you do with it? Can you compute with it? Can you do something fancy with these 2 to the n amplitudes that are running around? Can you actually use that power to compute things better than we know how? Okay. Okay, so that's the question. We're gonna proceed with that. So let's remind ourselves: a state is a vector of 2 to the n amplitudes, one for each pattern of n bits. It could be this vector. You can just write it as this vector. The Dirac or bracket notation is the amplitude of 0 is this bracket. So the state is written this way. That's just the notation they use, so we'll use that too. You can think of it as just a vector. It's just a vector of these amplitudes. Okay, the alpha x is the substring that's here. Okay, so now what's the idea with a quantum computer? Your input is an n-bit string, and what you do is you put it into some quantum computer, which really, maybe is a state on many with many numbers. This particular horizontal bar corresponds to maybe 2 to the n numbers, or 2 to the n amplitudes. Okay, so now this is not to scale. If you go from n to 2 to the n, this particular thing would have to be larger than the size of the universe to some large power. That didn't fit on the slide. So, but you have to imagine this is very, very large. Okay? And then what you can do is you can move from one state to another doing some quantum operations, which we're going to talk about in a minute. And you can go through a circuit, and then at the very end you can output, you can measure. And then what you get back is n bits. So as far as you're concerned, you only ever put in n bits and got out n bits, but somewhere in the middle, this big quantum computer was doing some operation on a lot of amplitudes. So it's sort of exponential. So those middle bars should be exponentially large, which obviously I can't put on the screen. And if you do this, we can, it was shown that you can factor in polynomial time. Okay, and we'll show you how to do that. Okay, and you can't watch this. This is unseen. We don't know what's going on in there. If we ever look at it, it collapses. It's a mess. Okay, the measurement is random. Okay, this is okay as long as the answer is right with decent probability, the ultimate answer you get. Why is this different than probability? Now that's the question, right? I mean, it could be that what's happening in this middle is that just a lot of, only one thing is happening, but each one is happening with certain probability. You could generate lots of possibilities, but, it's a partial measure changes remaining state. That's also there in probability. If I look at a few of the bits as they compute, then I have some conditional measurement on the rest of the bits. But the one thing you can do is you can add and subtract and scale amplitudes using quantum gates. Now this adding and subtracting and scaling of amplitudes is different than what can happen in probability. Probability, it's sort of hard to manipulate the probabilities in this way, particularly subtract them. Okay? Yeah, it's totally not clear how to do this for probability. Okay, so now you have, so let's talk about the quantum Fourier circuit. What its input is a set of 2 to the n amplitudes on x. And the output is also, in some sense, the output is maybe misinformed, but this is in this middle part of the circuit, right? So you have the circuit with an exponential number of states. You do the quantum Fourier transform, and you get another exponential number of states. Now, you can't actually look at all of these numbers. What you can do is do a measurement and get one output. Okay, so and this output is the Fourier transform of alpha, just the same one we saw before. So an n-qubit circuit is computing on 2 to the n amplitudes. Remember that, right? This is what's really happening. Okay, so randomized computations can't really compute on probabilities. And now a measurement gives x with probability p beta of x squared. So it's not like we get all of these numbers out. What we get is an internal state that we can measure. And what we will get is we will get x. We will get some value x. And the probability we got that value is beta of x squared, beta sub x squared. So we want to make it be such that the x we want it to output is sort of very informative and has a good probability of being informative, where this is the notion of the probability of that x. Okay, you have no access to beta x. All you get is beta x back. I mean, you can get beta x by repeating, and then you can measure the probability you got x. But yeah. So this is what it says. So this is quantum Fourier transform sampling. So output is 1x, even though that's where we get to deal with it, right? If we were actually even given 2 to the n numbers, we wouldn't know what to do with them. We can't remember them. We can't deal with them. What we get is one number back. Okay, so classical functions are f of x. So quantum, there's just a technical thing that quantum copies the input and computes f of x. So what it does is if the input is this, here the x is encoded in the input register, and there's some string of zeros, which may be the output, that the output will be that f of x. It's just the way it works. It's you know, pictorially, you know, pictorially these are all fine. So this says if you just put a gate that computes f of x on the circuit, right? You add the bits, the first 2 bits. So what you will get here is you'll get the same x here in both places. They are copied. And what you'll get is you'll get an amplitude for this value of x with the value f of x there. Okay? And it operates on all of the states at the same time. Okay? So every x is considered to be operated on by this function f of x. So the state transforms from alpha x to alpha x on the state x0 to alpha x on the state x f of x. Okay, so that's going to be important. So now, you know, if you read off, for example, the first x bits here, the first bit x, what you know is the last bit is going to be f of x, even without looking at it. Okay, so this is sort of the picture. You have a bunch of bits that are going in, and again, this gate is operating on all the alpha x's. Every x it's operating on, and it's going to change the alpha x in some way. Okay, so so what you get is you're putting in to the n amplitudes or numbers, complex numbers, and the Fourier transform of amplitudes. So you measure, you get each n-bit string y with probability beta y squared. Now the Fourier transform sort of multiplies by m of omega 2 to the n, right? So this m of omega 2 to the n is this matrix representation of the Fourier transform. 1, 1, 1, 1, 1, 1, omega, omega to the 1, omega to the 2, all the way to omega to the 2 to the n, where omega is 2 to the nth root of unity. So it's just multiplying this matrix. Now this matrix is 2 to the n by 2 to the n. It's a little shocking, right? So this 2 to the n by 2 to the n matrix on this is 2 to the n, right? This is of length 2 to the n, so that's what you're multiplying here. That's this figure, this is the alphas here. And alpha there. Okay, and then out comes the matrix beta, the vector beta. Okay, so the gates are not just operating on the bits and keeping the amplitudes the same based on that bit. Like if you map, for example, if you have all zeros and all ones and your function maps, you know, does something to those bits. Here, I'll show you an example in a minute. Okay, so multiplies by m omega with only n squared gates. So somehow it's dealing with all these 2 to the n amplitudes, but the number of gates actually uses n squared, because really these wires are going through and you're only building gates on these wires. I'll show you in a minute. And that's changing all the amplitudes. It's operating on all the amplitudes here, okay, on any pattern of bits. Okay, the size of the circuit is polynomial. Wow. So the gates act on all the states in parallel, just like randomized computations. This is not so surprising if you think of every input is, you don't know what the input is. Every input is operated by gates, but it just acts. I mean, we could view that setup. You can view as randomized computation. What you can't do is actually figure out how to do this particular multiplication with randomized computations. You can compute and even subtract with amplitudes, which randomized computations can't do much. So randomized computation is a good view, because thinking that the bits that are running through your wires, you don't know what they are. That's reasonable. But the thing that the power it doesn't have, the quantum does have, is that when you have amplitudes on different patterns of bits, they behave differently than probabilities on different patterns of bits. Okay, so FFT, what does it do? You know, if you take the 16A view of an FFT, one view of it is that it tries to find the period of a periodic input. So if I had an input here that was 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, that's periodic, right? And now, and I mean here, this is alpha all zeros. This is a sequence of alphas. Alpha all zeros, alpha all zeros and a 1, and so on. So it's periodic in these alphas, okay? Because we're doing the Fourier transforms on the alphas, on this vector. So if that vector has a periodic nature, for example, the alphas had this pattern, its period is 4. You can notice that in the outputs here. One of these outputs would pick up, oh yeah, there's a sine wave of length 4, which is highly correlated with these ones. That's what the FFT does. That's from the FFT 16A view. Okay? Okay, so now let's go and think about factoring. Okay, that's our application. So we want to pose factoring as a notion of finding a period, and basically it's natural. If x is a non-trivial root of 1 modulo n, then the GCD of x plus 1n is the non-trivial factor of n. Okay, so maybe I should do an example first. In some sense, this follows from this non-trivial square roots. Okay, so if you had x squared is equal to 1 mod n, you know that x plus 1 and x minus 1 is equal to times x plus 1 times x minus 1 is equal to 0 mod 1 mod n. Now, if x is not equal to n plus 1 and x is not equal to n minus 1, then this says that this implies that if you put in x was n plus 1, you would get this is n, which is 0 mod n. So that's a trivial root. These are the trivial roots. Okay. So now, if it's not one of these, then x must be something else. And if x is something else, then the GCD of x minus 1 and n must not be 1, right? So the x plus 1 or x minus 1, at least one, probably both, have a factor have a common factor with n, which is less than n. Okay, so if n is an odd composite, then if for at least half of the x's, either GCD of x of n is not equal to 1, or the order r of x is even, and x to the r over 2 is a non-trivial square root of n, of 1 and mod n. So first of all, if you guess an x which has a non-trivial, if there's an x such as GCD of x and n is not equal to 1, you're done. You've factored in. You at least found one factor. That's this case. Okay, the other case is that x to the r over 2 is a non-trivial square root of 1, which means x to the r over 2 plus or minus 1 shares a non-trivial factor with n, and then you can use the Euclid's algorithm to find some factor of n. Okay, so here's an example. This is the example of the non-negative square roots. 4 squared is equal to 1 mod 15, so either 4 minus 1 or 4 plus 1 are non-trivial factors of 15. In fact, both are. 1 is 3 and 1 is 5. So what would happen is either you would find an x where you already find a non-trivial, like 3, for example, or for 4, the square, it's a non-trivial, it's not 1, or it's not 4 is not equal to 1 plus or minus 1 mod 15. So it's a non-trivial square root. So finding one of those also gives you a factor. And it says this particular factor will always produce. For anything that's x to the r over 2, for half of the guys will be a non-trivial square root. Okay? Okay, so roots and unity in Fourier transform. Okay, so we start with this state. So that's not already, that's kind of not easy, but we'll discuss a little bit how to do that. So what we do is we're summing over these brackets for all the values of a. Now this is m here is 2 to the n. So a is any possibility of any a is of some n-bit string. 0, 1 to the n. Okay. And big M is 2 to the n. It's just the scaling factor that you want to have the total amplitude to have the sum of the squares be 1. Okay, so now what we do is we compute the following. That's fine. We can just write a circuit that computes f of a, and f of a is x to the a. Okay? Okay, notice x is in there. We took a value x. This is a random element from 1 to n minus 1. Okay, so this is a random element from 1 to n minus 1, x. Now, the function we're computing is x to the a. So we can write a circuit to do, for example, modular exponentiation. So this would be mod n. Okay? So now what we have is we have a bunch of wires, right? And on these we have a, and on these we have f of a. Okay? But that's not what we actually have. We have this a with amplitude alpha a, and we have this f of a with amplitude alpha a. I mean, actually this amplitude is for the whole configuration. Okay? So that's what happens, right? For each a, we have 1 over root m times alpha a. Okay, so now a is really it's just a number, right? This is just a number, okay, as well. Okay, which is something you just think about it as a number, right? Because what we're trying to do is we're trying to have every value. So what we've done for every value of a, 0, 1, 2, 3, up to 2 to the n, we have some alpha a in this exponential sort of state. We have an amplitude for every value from 0 to big N of x to the a. So what we have in particular is we have x to the 1, x to the 2, x to the 3, x to the 4, x to the 5. Now, one of these x's, now at some point x to the r should equal x to the 1. Okay? And x to the r plus 1 is equal to x to the 2, and so on. Okay? So what it says is that when we measure the second register, f, we're measuring these, we have a here. We have f of a here. We measure this. So now the amplitudes collapse. So the amplitudes collapse only to the a's that are consistent with this value of f of a. There is no amplitude on if f of a equals x1, then we could have x1. We have a non-zero amplitude on x1. And if r is equal to 5, we may also, 4, we have a non-zero amplitude on x to the 5th and x to the 9th and so on. Okay, so that's for, yeah, okay, so that says, now the first register, this is this one. It used to be uniform for all possible values of a. Now it's uniform for all possibles of a whose function value is equal to f of a. Okay, and that has period r. That has the periodicity of this value x, which we're assuming to be less than n, big N. Okay, the resulting alpha has non-zero amplitudes with period r. Okay, so it says x to the a is equal to z for a equals j, j plus r, j plus 2r, and so on, since x to the r is equal to 1. Okay, So QFT, the quantum Fourier transform of a period K signal, gives you a periodic signal of m over K with zero shift. So we do several times. So we run and measure the quantum QFT. The result is a multiple of m over r. Okay? Because what it's going to do is going to give you the period of this function, which and there's many periods. There's the r, there's 2r, and the 4r, and the 3r. Those are all periods of this function. And so it's going to give you, the QFT will give you back one of those periods at random. So now you can compute the GCD of those results, and it will likely be m over r. It's very unlikely that you will get m over r, 2 times m over r, 4 times m over r, or whatever, right? So it will give you, the GCD is unlikely to be, sort of accidentally have a bigger period. So the order of x is r. You can compute r, and then you can just check GCD of n and x to the r over 2 plus 1. This is a non-trivial square root if r is less than n, and you check the GCD, and that will give you a factor of n, a non-trivial factor of n. Okay, so you need the period to derive m over r. There's some sort of details here that don't actually work out if you actually follow this exact outline. So that has to be cleaned up, because m is 2 to the n, so r has to be sort of nice for that, but that's okay. Okay? Similar ideas. This is a basic idea, and then you crank away and other things happen. Okay, so now we saw how the quantum Fourier transform, this notion of converting from the alphas to the betas with a Fourier transform on 2 to the n amplitudes. That's what we're doing it on. Right, and so, what do the gates look like? Okay, so here's a very fancy gate. What it does is the following: it's a Hadamard gate. What it takes in is a bit, and it will produce a superposition of the state 0 and the state 1 with 1 over root 2. It's a Bell. It's not a Bell state, but it's just a uniform superposition there. And this is also a uniform superposition, but it has a negative sign here. Okay, this is not something you can do with probabilities, right? There's no negatives there. But the Hadamard gate can produce these complex amplitudes. Negatives are certainly complex. These numbers don't, so far I've only used real numbers or even negative numbers, but they could have an I on them, plus I. Okay, so now the Hadamard gate of H alpha 0 is just that. It's just you take this Hadamard gate and this Hadamard gate, and it's linear, so you add them up. So that's the plus and the minus here is where this minus corresponds to this minus. Okay, so you added amplitudes and even subtracted amplitudes. So this is kind of fancy. This is not something you can do if you just had a 50-50 coin on 0 and 1. You can't sort of manipulate the situation to not do that. Okay, just if you want to have fun with geometry, this is just, you can think of the x, you could write your amplitudes alpha 0, alpha 1 in the xy plane. And the Hadamard gate takes this angle here and just reflects the point over that. So that when you view it that way, for example, this is 1 here. That's 0, 1. It gets mapped down to here somewhere, which is just a reflection over this line. And it's nice to see it that way because you see that the Hadamard gate is its own inverse. Okay, another kind of gate is called the controlled NOT gate. So the controlled NOT gate, if it takes in it's a gate on 2 inputs. This is a gate on 1 input. Okay, this is a gate on 2 inputs. So you can grab 2 of your wires and you can put them into this gate, and you get 2 wires out of this gate, and what happens? If and the controlled not says if this first bit is 0, the output will do nothing to the second bit. It will still be 0. Okay? If on the other hand the first bit is a 1, it will flip the output here to a 1. So controlled not. The first bit here controls whether you flip the not the second bit. That's what it says. So for example, if you operate on such a, in fact, notice that again, with these two wires, it's not that you're operating on 2 fixed bits. You're operating on all of the possible bits with respect to their amplitude. So what this does, this controlled not does, is it produces a new superposition. It's say it started with this superposition that looks like this, where it switched this amplitude and this amplitude. So you can kind of move the amplitudes around. Okay, so that's very nice, right? So these are numbers that you can add, you can subtract, you can move them around, and you know, it's like wow. Okay, so now what does a quantum Fourier transform look like? Now let's remember the Fourier transform. We split into odd and even inputs and recurse on 2 subcircuits. So you combine x0 and x1 from the subcircuit. So what happens is okay, so what you do is you have all these roots of unity, and here the n will be 2 to the n here. Okay, and now what you do is you have the odd polynomial, which is the odd degree coefficients, and then the even ones, and you will compute the Fourier transform on them, and you will get back 2 values here, both the value of the output at I and the value of I of n plus n over 2. Now the reason I wanted to show you this in detail was this: you just add omega I times this output, and here you add negative omega I times the same output. Okay, here these two are also the same. So in some sense you're computing 2 values with 2 values, and the way you're combining them is you're adding a phase, this is this phase, times this other value, or you're subtracting the phase times this other value. Okay, so the runtime recurrence is that, and n log n, but in our case, this n would be 2 to the n, so this would be 2 to the n, which is a disaster. You can't do this because we're working with 2 to the n amplitudes. Okay. Okay, so now, okay, so here we're going to split. We ignore the low order bit. That's our split. Okay, it's really funny, right? Because now what we did is we used to have n wires. Okay? And now we're just going to say, well, there's an amplitude on every one of the 2 to the n bits. Now if we ignore this first bit, then the amplitude on the n minus 1 bits, they're the same. They act the same, whether the algorithm for them is the same, regardless of whether they are have a 0 in this first bit or a 1 in the first bit. The algorithm that you process each amplitude with in this on these n minus 1 bits is the same for here, right? So that says for half the values you're going to, which is exactly 2 to the n minus 1, those are half the values, you're going to do the same thing whether they become with a 0 or a 1. It's the same algorithm, right? Whether they're 0 or 1, you're still running the same circuit here, right? This A0, it's just the FFT on half the inputs. This is also the FFT on half the inputs. So the amplitudes of both will be processed in parallel, whether the low order bit or the high order bit is 0 or 1. So then you build one QFT circuit on n minus 1 bits. So these n minus 1 bits has a QFT circuit, and it does the action of both of these, because in parallel it's dealing with the amplitudes for these bits and the amplitudes for these bits. Okay, I mean these configurations. So they will work on amplitudes of the string for both x0 and x1, and for all x. Now, how do you combine these things? Well, this is the combination, right? So you're doing this thing. You combine the amplitudes of x0 and x1 in a fancy way. So you remember the output here is alpha 0x plus or minus, in these two cases, is either plus or minus the value of this thing. I'm ignoring the phase for a minute. Okay? Okay, so that's it. So basically with the Hadamard gate, that's exactly what the Hadamard gate does. If it's a 0 bit, it will add it as a plus. If it's a 1 bit, it will add it as a minus. So it will do the right thing with the amplitudes recursively. Okay, so we need to do more than this, right? You need to multiply by this. Okay, that's the phase. Okay, well that's a bit complicated, and we can talk about it, you know, in office hours if you like, or you should see the book. But that's more complicated. This only took one gate to recombine, but to actually multiply by the phase takes some more work. Okay, and so there's another kind of gate called a conditional phase gate, and that's what's used in these phase multiplications. Okay. So the total size of the circuit is, you use O of n gates here to apply the phase at this outer level of recursion, and then you have the recursively smaller circuits that compute all of these for you. Okay. And that's it. And that's the quantum Fourier transform. And yeah, thanks for listening. I hope you enjoy your holiday.